Okay, hello again, folks. You remember in the last video, we learned how to derive a rate law from experimental data. Now, this video follows on from that one, and it's how we derive a mechanism from a rate law. Okay, so it's a three-stage process. Experiment gives us the rate law, and the rate law enables us to propose a mechanism. And you remember that in the last video, we had substance A reacting with X, producing AX, and experiments led to this rate law. And this rate law told us that the rate was proportional to the concentration of A and was independent of the concentration of X. There was no involvement of X. So now we have to use our rate law to try to propose a mechanism for the reaction. And a mechanism has a number of steps, and those steps have to add up to the overall equation. Okay, so this is the information that you need here. A reaction mechanism. It's a step-by-step description of a chemical reaction, and each step is an elementary step or an elementary process. And the reaction mechanism that you're proposing must do two things. First of all, it must add up to the stoichiometry, the Barth equation. And secondly, it must obey the rate law that was determined experimentally. Okay. Now, this is the overall reaction for the reaction between A and X, and we saw this in the last video. And the proposal is that the reaction has two steps. The first step is unimolecular, one particle, and it's the slowest step. It's the rate determining step. It determines the overall rate because it's the slowest. And you get this high energy intermediate. And then in step two, the high energy intermediate reacts with X to give the final product. And that step is bimolecular. It's got two particles involved. Now you can see that if I double the concentration of X, A rather, if I double the amount of A in a given volume, then there'd be twice as much of this intermediate produced. So the reaction speed would double. But you can see that if I increase the concentration of X, it's going to have no effect whatsoever because this X cannot do anything until this slow rate determining step has occurred. So you can put as much X in as you like, and it's not going to affect the rate. Whereas if you increase the concentration of A, there will be an effect because this is the slowest rate determining step. Now you can see if I cross these out, this intermediate, you can see I end up with the overall equation. Therefore, I've satisfied the Barth equation. A plus X gives AX overall, and I have satisfied the rate law because X is not involved at all in affecting rate, and doubling the concentration of A would double the rate. Okay. And now you see this kind of picture before. These cars can go as fast as they like, but the rate determining step is when the person takes the money at the toll gate, takes the ticket and lets the car through. If the person says, I'm going to sit down and have a sandwich or a cup of coffee, those cars are going nowhere. So the rate determining step is really how fast the money is taken at the toll gate when they actually go through. Okay. Now, when you derive a mechanism, I've already said the mechanism has a number of elementary steps, elementary processes, and the sum of those must equal a balanced chemical equation. We've said that already. And it must agree with the observed kinetics, okay? And the key thing is the slowest of the steps is called the rate determining step, and it determines the overall rate. It affects the overall rate, okay? This bit here, I'll explain in a moment. The slowest step, the rate determining step called the RDS, the rate law of that step is the same as the overall rate law, because when you look at the rate law of a step, you're actually looking at which particles collide. But when you look at the overall equation, you're not looking at which particles collide, okay? So the proposed mechanism, going back to that now, we agreed that the overall equation is obeyed and the rate law appears to be being obeyed. And the mechanism that I proposed on the previous slide, this mechanism that I showed you here, it suggests that if you doubled A, you would double the rate, and that X would have no effect on it. So that's kind of satisfied it there. And the rate law of the slowest rate determining step is the same as the overall rate law. Okay, I'll do that on the next slide. It satisfies the overall balanced equation as well. So here we go. Here's the actual. This is showing what particles actually do. Right? It's not a balanced chemical equation. It's actually showing an elementary step. And you can see there's one particle involved, so I can put a 1 there, okay? And here's the rate law, and you can see that if there's one particle there, there has to be a 1 there, okay? They are matched there. The rate law for the RDS, rate determining step, is the same as the overall rate law, and you'll see that again now in another example, okay? So let's recap what these elementary processes are. They are usually unimolecular or bimolecular. A trimolecular step is very unlikely. It's statistically unlikely for 3 particles to collide. The exponents for the concentration terms are the same as the stoichiometric factor. So what I mean by that is there's a 1 here, isn't it? The stoichiometry is 1 there, and the exponent is 1 there. Okay? So the exponent for the concentration terms in the rate law are the same as the stoichiometric factor in the elementary step. Intermediates are produced in one step and consumed in another. So we can go back here, go way back here. That is produced and then it's consumed. Okay, so we've covered that. And one elementary step is usually the slower than all the others, and it's known as the RDS, the rate determining step. Okay, now here's another example. We have A reacting with 2B, and it gives us AB2. This is the overall balanced equation. We do not know who is colliding into who. We don't know what the particles are doing. We only know that this is the overall balanced equation. Okay? So we have to determine the order with respect to each reactant. Now let's suppose the person did the experiment. And of course, they have to find the order with respect to A and the order with respect to B. And the overall order is going to be the individual orders added up. Okay, the overall order will be this exponent plus that exponent. Now let's suppose they found this, and you should already know this is telling us the reaction is first order with respect to A, and there is the rate law for A. That's just for A with respect to A. Okay, and let's suppose they found out it was also first order with respect to B. So we've got 2 reactants and it's first order with respect to both, and that's quite possible. Okay, so here we are then. Here's the balanced equation, but here's the rate law. And once again, you can see there's no connection between the rate law and the balanced equation. There's a 2 there, but there's not a 2 there. They are not related. Okay, so it's first order with respect to each reactant, and of course it's second order overall. Okay. Now, the reactions, as we say, is first order with respect to each reactant, second order overall, and here's a possible mechanism. Step 1, a bimolecular step that is the slowest step, the RDS. One particle of A bumps into one particle of B in the slowest step, and you get this intermediate, which I'll call AB there, right, the intermediate. And it's pretty obvious, I hope, that if I doubled the concentration of B, if there was another B there, there'd be twice the chance of a collision. So you can see it's going to be proportional, twice the chance of a reaction, double the rate. And if I kept B the same and I doubled A, there'd be twice the chance of A hitting B. So again, it would be first order with respect to A. So you can see that's quite feasible. Now, you can see there are 2 B's here, but I've only used 1 B so far. So the proposal is, in the second step, which is also bimolecular, this AB intermediate bumps into another B in a fast reaction, and you get the final product. Now you can see if I cancel out the intermediate, you can see I'm getting the overall equation. So I have satisfied the balanced equation. You can also see that this is the RDS, which dictates the overall rate. And you can see there's one particle of each one particle of each. If I double either of them, the reaction rate would be expected to double because there's twice the chance of a collision. And I can get this directly from the rate law. There must be one particle of each involved in the RDS. Okay, and there is the overall equation. And I show it here pictorially. Here's the balanced equation. There's 1A and 1B in a slow RDS. Here's the intermediate. It then reacts with the second B to give the final product. Okay, now then, here is the rate law. You know that this is moles per dm cubed per minute. You know that each of these are moles per dm cubed. Pause the video now and work out the unit for K in this second order reaction. Okay, I hope you've worked out that the rate constant must have units of dm cubed per mole per time. It doesn't have any physical meaning, but you have to have a unit for a constant if it's placed in the equation. The unit is dm cubed per mole per time, in this case per minute. And I usually tell my students either memorize it or simply work it out again in the exams to make sure you know how to derive those units. Okay, so here we are, balanced equation, the rate law, and yet again you notice there's no relationship between the two. Okay, and once again there's our mechanism that covers the whole thing. Okay, in this case the first step was the slowest step and is the RDS, and it determines the overall rate. And my proposed mechanism is feasible because one, it suggests that doubling A or B will double the rate. The rate law of the RDS is the same as the overall rate law, which we'll have a look at on the next slide. It satisfies the observed kinetics and it satisfies the overall equation. And here we are. I am literally looking at a collision here. So I can take the rate law straight from this because it's an elementary step. One particle, one particle, one particle, one particle. And this is also the overall rate law, isn't it? The rate law for the step is the same as the rate law for the overall reaction, second order overall. Okay, now this is interesting. We'll just finish with this. You can see there's one possible collision here, isn't there? Okay, if I doubled B, it would be twice the chance of a collision. If I doubled A, there would be twice the chance of a collision. So you can see it's first order for either. If I doubled the concentration of both, I'd get this situation. Now, how many collisions are possible? Pause the video, work out how many chances are there of A hitting a B. Go, think about it. Yes, you can see there are 1, 2, 3, 4 possibilities. There's 4 possible collisions. So if you double the concentration of both, the rate would go up 4-fold. If you go up from this situation to this situation, you're going to have 4 times the possible collisions. The rate would quadruple, okay? And we can see it mathematically like this. If these are both 1 molar, if they become 2 molar, you can see that, of course, K is a constant, you can see that 2 2s are 4. So the rate would become 4 times bigger than it was, okay? You can do it mathematically or you can do it pictorially, okay? And once again, a reminder that if you're literally looking at an RDS, you're literally looking at who's colliding with who, and you can get a rate law, you can get the overall rate law straight from it. So 1A and 1B, you're going to write that. If there were 2 A's involved in some sort of reaction, you'd write K times A squared, okay? And here is a summary slide. This is a general slide, okay? For this reaction here, the rate of the reaction is K times A times B raised to particular powers, these exponents, and those are called the orders of reaction, okay? And a quick look now, first order, you know, is 10 to the minus 1. 0 order is the same as the unit of rate. Second order, we just did it, is dm cubed per mole per time. And third order, you can pause the video and you can try to work out what the units would be. Think about it now. And yes, the unit is dm6 mole to the minus 2 per time. And we'll deal with third order in another video. Here are some examples of real reactions. And here are the rate laws. And you can see there's no relationship to between the rate law and the overall equation, okay? And here is a summary of the units of k for different rate laws.